Hello, this is Keao Caindec with Mocana, and welcome to our webinar. Please, welcome, and if you're joining us again, welcome back. Today we have joining us from Mocana, we have Srinivas Kumar, our VP of Engineering. So welcome, Srinivas.
Thanks.
Today we're going to be talking about automated security lifecycle management. Wow, that's a mouthful. What that is when you think about an IoT device or that you may be manufacturing or using, or an embedded device in an industrial device or something like that, you need to think about managing security. Everything from implementing an identity on the device to updating the security to managing certificates, both provisioning all the way through to revocation. So security lifecycle management when it comes to IoT can be quite complicated because they're different than typical IT devices. And automating it is critical to being able to scale that. So this is part of a series. The second part that we'll cover today is on updating devices. So, Srinivas, let's get started. Okay. So, a little bit of an intro to Srinivas. Srinivas heads up engineering as our VP of Engineering here at Mocana. Previous to this, he was the CTO of Tessera, which he founded also Tassware in 2011, which was acquired by Tessera. He has also been an EIR at SRI and has held executive positions at a variety of companies. When he's not working here at Mocana driving our engineering innovation, he can be seen inventing and issuing patents, apparently. Welcome, Srinivas. Before we get started, I wanted to point out something that I found interesting, and that is a brand new report that MITRE put out. MITRE, as you may know if you're in the security industry here, among other things, manages the CVE database that tracks vulnerabilities, computer vulnerabilities in both hardware, software, and a variety of embedded devices and systems. So they track a lot of that, not unlike ICS CERT, which is under Department of Homeland Security. The report was called Deliver Uncompromised, and it just came out, I think maybe last week. But it's a great report, and it provides a lot of terrific recommendations on what we can do to improve security on devices. Now, what caught my eye was they said software is the new hardware. So when we think about updates, you know, software in devices today is really becoming the new hardware. It's everything. That's what enables the device. And according to MITRE, increasingly, software developers are relying on third-party components. And should adversaries insert malicious functionality into open source components or software code to exploit latent vulnerabilities, the resulting corruption of the software tool chain can have pervasive and durable effects. These may not result in immediate harm, but can be activated at the time chosen by an adversary. And we've seen this happen across many sectors, right? Whether it's in the industrial sector like Stuxnet or Black Energy in the Ukraine, to more recent attacks on industrial systems or IT systems in manufacturing environments like NotPetya. But there's no question the devices today that are out there relying on software have vulnerabilities, and we need to figure out how to protect them. So that's what we're going to talk about today. So software updates. Srinivas, I get my Microsoft software update recommendation. Is that what we're talking about? when we talk about IoT? How is it similar or different when you're thinking about updating devices versus PCs and laptops?
Yeah, the fundamental difference in updating a user-based system is the user interactivity. You don't want a Microsoft update to happen without your consent at the time of your choosing, right? And that's the fundamental difference. It's not a forced push on you. Secondly, as you know, if you're familiar with how Microsoft updates have been historically, not all updates will successfully install. And on a headless device, you cannot have that unpredictability about did the update actually go through. So how do you actually validate that the update was applied? It's very common in Windows, for example, where if you push the updates to a bunch of devices, some devices may not update properly and it rolls back. So you cannot have that type of an indeterministic state in IoT devices where some devices were updated and some were not. So that's basically the first issue. The second issue is who is pushing that update. Now you're accepting this update because you have a trust in Microsoft. They own the platform and you trust them to do the right thing. But what also happens on a Windows device is you're applying other updates that does not come from Microsoft. It's your IT admin or the end user with administrative privilege who might update an Adobe Reader or they may update some other application. So there are multiple updates coming from multiple providers and it is all really configuration management based on your policy. The IT administrator has a policy, the company has a policy, and so it's very complicated. It's all about people and process. In the IoT device, it has to be automated, it has to be unattended, and it has to literally be zero failure. That's where the fundamental difference is.
So you talked about a headless device, and I want to talk about that a bit more. So updating the firmware on a device, an embedded system, what is a headless device?
A headless device is something that is running out in the field within a environment like an industrial control system or energy infrastructure and so on, where no technician can be physically at the device. The device can be remotely reset, it can be remotely managed, and there is no interactivity in a sense of a keyboard, mouse, or a user.
So there's no GUI or keyboard or
right.
or anything like that.
Right.
You can access it remotely.
Right. It's a non-interactive device. Mm-hmm. And it may also be set into an autopilot mode, where it has to figure out how periodically it needs to go and get updates for itself. Mm-hmm. It's what we call as a data dioding. You don't want inbound access into devices because it's impossible to control the factory default passwords or access passwords when you allow a technician to telnet in or SSH in and so on. So that's just not an option in a lot of air-gapped and protected IoT devices.
So when I get a request from Microsoft on my laptop to or on my Mac to update it, that is quite something that I can control, right? With these headless devices, when that update is available, I guess the trick here is how do you control it? So how do you update? What are the different ways of updating software on these headless devices typically?
Right. So as you see on this screen, where you see one optional update. Now these are the situations where every IoT device is going to be different. There's not going to be a one-size-fits-all. It has to be policy-based, it has to be profiling-based, and it should be based on the environment. For example, if you're updating a valve or a controller or a compressor in a production system, the policy that decides when the update needs to happen will be tied to, is this machine in operation right now? And what happens if this operation fails? How do you roll it back? Do you know the exact model number, serial number, vendor? So you know that you're pushing the exact correct update to the device. Now you don't want to send a Sony update to a Panasonic TV and then figure out that you cannot reverse it. And we have had cases where updates were sent to devices in the wrong country, causing irreplaceable damage. So those are the factors that you have to apply it as required. You have to apply it based on the type of device, and it has to be policy based.
Now, so like, these devices, some of them you could just pop in a USB stick, right? The USB port is active, and maybe there's a button on it or something like that. You put in the USB, it recognizes the firmware, it downloads it, or you access it remotely, and and then you have the USB. That seems very vulnerable to me, being able to simply connect to the device with the USB and update the software.
Yes, so that makes auditing more difficult, because being able to authoritatively say that the USB stick was validated and the person who was using the USB stick was authorized requires a lot more auditing compared to a sealed system where over the air or over the network updates can be managed.
Okay, so over the OTA or over the network, one scenario here is where the update is requested by the device. So say it's a thermostat in your house, right? These things, all of a sudden they'll say, there's an update available, and you should, do you want to install it? How does that work? What is the mechanism that's working? What's implemented on that device?
So those type of updates can happen in one of two ways. Either it's a push or a pull. So depending on the application, you can have a push mechanism that remotely forces the update based on policy to the device. The other option is a pull, and the pull can also happen in the form of a signal, whether it's a message pops up bus or a SMS text or some other means that already exists with the service provider to send a message to the device that it needs to dial home and get itself an update. So depending on whether it's a wireless carrier-based system or a service provider who is doing a managed services kind of update, those mechanisms will change, but fundamentally it's either a pull or a push.
Okay. Yeah, and we've seen that with either these devices here, or even if you're on a factory floor, you may actually end up downloading it to a technician's laptop, and then going into that private network there, being physically close, and then pushing the update to that device.
Right. Now there are two types of updates. Some of the simpler updates are at application level that you can do remotely. As you see here, with there are cases where a device might get into a situation where a firmware update is required, and a lot of the secure boot devices require human intervention by literally holding a switch down and using a recovery image from a USB stick. So when you get to that situation where, let's say you have a cyber attack and your boot loader is compromised by the attacker. Now at that point you cannot do a remote update. So you need to have a self-defense mechanism all the way from power on, that even if your boot loader is compromised for whatever reason, you can still remotely update that device, and that's really where Mocana can provide at that level remediation in a way that you can even recover a root partition through a recovery partition. So it's not just an update of a device in normal operation, but a recovery of a device that may have been compromised.
Interesting.
Which is very important in infrastructure play, because let's say you have a cyber attack organized by a rogue nation on, let's say, parking meters in a city, let's say New York City. How are you going to recover that? You really need that kind of an emergency lever that says no matter what level the compromise is, we still have a way of remotely recovering the device. And that's really where the bar has to be raised when it comes to IoT, because these are service impacting downtime. Like unlike IT, where if your laptop is compromised, you can get another laptop and you have a ghost image, or you can recover it very quickly with an IT admin. But in the case of an IoT device, the service impact of traffic lights turning off or transformers blowing and automation systems being held hostage, the consequences are disastrous.
So Regardless of how these updates are being implemented on the specific device, let's talk about what some of the challenges are with a lot of implementations of a software update mechanism in these devices. Can you talk about what you see as some of the limitations or weaknesses in how updates get implemented today?
Yeah, so it really starts off from the supply chain, making sure that the source or the origin of the update is authentic. And that will be achieved through a proper signing mechanism. And when it comes to the signing mechanism, based on the standards, based on your customer's requirements, compliance requirements, the strength of signing, the national laws, international laws in terms of import, export, ciphers, all that come into play, right? So you have to be mindful of, is this update coming from a very specific country where the device was manufactured, and how are they going to deliver a cryptographic signature that may have import-export restrictions. So these are some of the things that qualify the authenticity of the content even before you apply that content. And so that's the first step. The next step is mutual authentication, all the way from the device being able to authenticate itself as the legitimate device that qualifies for that update, and the sender qualifying themselves to the device, because what can happen in an IoT world is also the theft of intellectual property with clones and counterfeits, where you would be delivering content to a clone or a counterfeit device where your code can be reverse engineered, right? So there is an authenticity of both players that is important.
And when you talk about that, this is really more machine to machine or client to server mutual authentication, not kind of password authentication, right?
Yes, so this is strong authentication based on trusted ID, based on a domain and certification. So look at this as encryption domains. It's not very far. If you look at what Microsoft has done with the way they did updates, is that if I download an update to my laptop, it allows my laptop to become the primary source for them to update other laptops in my network. Now, this is something that could become reality with connected cars, with blockchain, where there will be multi-hop, primary to secondary. A lot of these air-gapped devices can never reach out to the source. So there will be an intermediate point, a gateway or a primary. So mutual authentication becomes important because now you're getting your updates from a proxy. Right? So that's basically, the updates are something that will become a multicast kind of updates too. You may get an update through connected cars. Right? So these are all the things that will change the way software is delivered in the future.
So talking about this, you know, I know we've talked about this before, but this notion of just hash and sign, what are some of the strengths and weaknesses of that in how it's deployed? For example, is there a difference between where, you know, how you authenticate versus maybe just storing a public key on a device? You know, what are the pros and cons of ways you can use hash and sign technology for verifying updates?
Well, the weakness of hash and sign is not just limited to the strength of the hashing. It also is a matter of tamper-proof delivery in a supply chain, because there could be a rehash and resign, and there would be no evidence that there was a rehash and resign, which means a distributor, a reseller could have tampered with original content, which cannot be caught because you lost supply chain provenance at that point. So it's almost like saying a bottle with medication was resealed. Well, you need to know that the seal was opened, something else was put in the bottle and then resealed. And that's really supply chain provenance. Was it tampered from origin through the chain of trust? And that's really where hash and sign is not adequate.
Right. So, for example, if I'm a software developer, I could hash and sign my code, send it to a manufacturer. They have my public key. So they can open that package up and find the original content, my software that I developed. they could actually then make changes and reseal it, and then put it back in, and the device wouldn't be able to rather than taking it and signing it again themselves.
Right. So it's really the transfer of ownership of that content, where content has gone through multiple hops, and the assurance that all the way from the provider to the distributor to the reseller to even coming inside of the enterprise, where multinational companies might have a corporate headquarters that might distribute it to regional offices, might distribute it down to the customers.
Right.
There's a huge supply chain, and it is very difficult to figure out if there was an insider threat.
Yep.
And whether there was any tampering.
So if I have compromised the private signing key of the original software developer, right? Somehow I've broken in, found the one key, or found found that, then I can rehash it and re-sign it.
Yes. Right, and it also because you'll be surprised how many times the end user depends on the OEM's key, and the OEM depends on the silicon vendor's key.
Mm-hmm.
And so the fact that you have an implicit trust, mm-hmm. and that the compromise of a private key could be something that could take weeks, if not months, to get disclosed, mm-hmm. Mm-hmm. Would also create liability for a lot of people in the chain.
Right. Yeah. This is the same whether you're talking about taking an update off of the internet and installing it on your printer, or someone compromising a device. If they have access to a single key that's used during this update process, you can load malware, right?
Yes.
If these protective mechanisms exist at all for validating and verifying updates.
Right. I mean, imagine X number of people pulling source code from GitHub and distributing it. Mm-hmm. How do you know that none of them were a bad actor? Mm-hmm. And that's really the fundamentals of the risks with anything that's open source, claimed to have come from GitHub, but could have been tampered along the way. Yeah.
And I mean, you talked about this a little bit, right? But a traditional supply chain, you've got devices going into a factory, being shipped, going into a store, being used by end users or consumed. The software supply chain, you have the source, many dependencies. You have integrators and other engineers touching that code. It goes in, is resident on some sort of device and deployed in a system. At any point here, you could interrupt this supply chain and compromise it, right? And as we talked about, if you have compromised the private key way up here, at any stage here, you can open it, rehash it, re-sign it, and it will look to the application like a valid update. Very, very challenging, right? So what we see in when we work with customers is, number one, oftentimes there's no security at all. If you can physically or over the network get access to the device, you are able to push any kind of update that you want to it. There's no application code signing. If there is, oftentimes they're using hash and sign, which is a very vulnerable approach because it's reliant upon one item being compromised to be able to break the system. And then you have many, many different points of entry where you can compromise and introduce malware. So let's talk about what we can do. So, when you think about these various scenarios and the actual devices, in this case this is a printer that's been opened up with an MCU on it on the printed circuit board. What things come to mind for you in terms of what we can do to really protect the supply chain more from an update perspective?
Yeah, the two things that are relevant here is validation by the receiving device, the complete supply chain provenance, in order to accept what is being sent to the device. And from the sender's point of view, checks and balances that this device is not a cloned or a counterfeit or an untrusted device. So that's really that mutual trust. that allows them to initiate this update process. And then the ability of the remote service to have a full traceability audit trail that the updates did happen, and you can generate a report that says this device is now in a known state with all the bits in the full stack, all the way from the silicon to the boot components to the transport stack and the key stores and configuration. Everything is as expected because the update has to vouch for the runtime and measured integrity of the system post-update, which is really the validation that the update was successful. Successful updates have to be measured, and that's really what we call as platform attestation. It's shipped from the factory in a known trusted state. If you apply a field update, you still have to audit it and vouch that it is still in a known trusted state. And that's really the important outcome of a successful update.
Great. Okay, let's talk about Mocana's approach to securing updates. So on the left here you have a connected device. This could be anything. It could be an IoT device. It could be some sort of typical device like a printer. It could be a server class robot. It could be an industrial control valve. So on this device we have certain software components from Mocana. And then you also have Mocana TrustCenter, which helps in this update process. Can you talk a little bit about how these systems work together to both protect it as well as enable a secure update?
So there are three tiers here. One is the device itself, which has clients. And then there is the middle tier, which is the services layer that deals with authenticating the devices and being able to push policies based on updates based on policies. And then there's a backend, which is the choice of the end customer in terms of the ecosystem. On the device, the enrollment client is the first agent that initiates the process of authenticating the device to make sure it's not a clone, not a counterfeit. Being able to provide a trusted identification of the device in order for a policy-based validation to be performed, and then a certificate to be issued to that device tied to its trusted identity, and then go to the next level of making sure that that issued certificate will only be enforceable by the enrollment client if it is in actual possession of a secret, which is called advanced proof of possession of a secret. So you have the device has to authenticate itself, provide its trusted identity, and be able to prove that it has a secret that qualifies the identity as really being valid. And so there's a lot of checks and balances.
And that secret could be in the form of a key hidden in silicon. It can be a key or certified keys within a TPM chip, or at a software level, it can be just an ID on the device that's somehow hidden.
Right. It can be any form of root of trust, whether it is hardware-based root of trust, like a TPM or a SIM, or it could be a software-based trust zone or memory enclave, or it could even be a tokenized artifact that is protected within some kind of secure store. So it's very flexible in terms of how you identify the device, because that will vary based on the form factor of the device. And then the same thing goes to the next level. Once the device has a certificate, it can generate various levels of certificates. It can be a platform certificate, it can be a device certificate, a ownership certificate, and an application on the device can issue a service certificate for itself. So now every entity on the device can have a certificate. And it's an automated protocol. It's an automated way of tying that chain of trust. The device watches for a root certificate. The platform attests to that. The application attests to the platform. So basically you have full chain of trust. Now once you get the certificates, the next step is the updates. With update client, now leverages the fact that it is in possession of various certificates that it can provide to the update service. And one of those certificates would be an encryption certificate that allows the update service to send an encrypted update back to the client. verifying that the client can now, with proof of possession of that secret, be able to decrypt it. So it's really a very strong checks and balances here, making sure that no single bad actor can cause a theft of intellectual property. And these could be a $5 device, it could be $1 million device. At the end of the day, updates cannot be sent to untrusted devices.
So first step, make sure that there's strong authentication with proof of identity, right? Or proof of possession of a secret. Number one, step one. If someone can attach to or connect to a device with minimal to no authentication, you're going to have problems, right? You have to solve that problem first. The second is being able to use standards, strong standards to update and secure the update that go beyond a simple hash and sign. PKCS 7 standards are one of the ones we used, very, very strong. And being able to have that leverage all of the digital identities, digital certificates that have been established in the first place. Great. The other thing I want to cover here is this notion of kind of when you have this system, right? You have this endpoint device, you have a gateway, you have a cloud. The benefits of I just want to go through the benefits again of this approach. Can you talk a little bit about that again?
Yeah. So in terms of the actual protocols and methods used, this is a very open standards-based approach. PKCS being a well-accepted standard, which allows for interoperability. The interoperability has to happen in a way that the device to gateway to cloud, the whole ecosystem can work, irrespective of who the cloud provider is, and also provides for multiple signers, which is critical in a supply chain, where there can be a provider, there can be multiple providers. Updates can come from various vendors, all the way from a silicon vendor to an OS vendor to application vendor. So this can be very complex updates, a full update package. That does require multiple supply chain provenances to be established. And that really provides not just a vehicle, but a process and something that fits into the workflow of companies that are dealing with IoT type devices.
Great. One of the things that I think is particularly interesting and important to go through is this notion of multi-factor verification. Earlier we talked about a single key being compromised, right? There's certainly reports of certificate store being compromised. Maybe someone running their own or self-signing certs and someone compromising that at their company, or compromising a single CA. Talk to us about this notion of multi-factor verification and how that works with TrustCenter.
Yeah, so just like in the user world, there's this concept of multi-factor authentication. This is a similar concept for a headless device, where it takes multiple signatures to be provided, where each signature is associated with a private key, the what is known as the what you know. And there are multiple entities involved, so it's not a single person. And by providing this type of multiple signatures, where each private key is stored with a different entity, it just makes it increasingly difficult for private key compromises and for a hacker or a set of hackers to introduce any kind of updates that can use compromised private keys. So this is really a multi-factor signing.
So in this case, let's say I'm a software developer, and I'm developing a software update to an infotainment system on a car that's going to sit on the infotainment ECU in a car. So the software supplier, they would take their software and they would use Mocana TrustCenter log in via a web client or running on their prem, and they would use that to package the update, which would sign it and then send it on to make it available to the next partner in that chain, like the manufacturer, right? And then that just continues along. With an ECU manufacturer, they can take it, validate it, they can wrap the, provided they get it, they're an authorized user of it, they can use TrustCenter to open it, test it, but then they take the original, still wrapped envelope with the original software update, and they sign it themselves, right? And then it keeps going down the chain. So what happens when the publisher, the systems integrator, or the dealer, auto dealer, the car, drive my car into the dealership, the car recognizes the network, it gets the update, gets pushed onto the ECU. How is TrustPoint and now working to take that envelope with multiple signers and open it? How's that working?
Right, so if the original content from the software supplier was tampered anywhere in this chain, then once the vehicle receives the update, it will verify all signatures. And if even a single signature does not match, it knows that there was some tampering. And that's really the strength of this. In fact, this is almost what blockchain does in a way, right? It's a cryptographic linked list. Somewhere down the chain, if somebody tampers with the content, it will break the integrity of the whole chain. And that's really what we're doing here. There's no single person can make any changes because they'll have to go back up the chain to be recertified, and that makes it tamper resistant.
Right. Right. And it's standards based, right? I guess there's this notion of pros and cons of blockchain versus standards-based multi-factor verification, right? This is more standards-based.
And it also gives the flexibility for each entity to pick their own signatures. The software provider might use an RSA 2K key.
Yeah.
The ECU manufacturer might say, no, I use ECC keys. So each point, you have your own choice of strength of your keys. And so you make up your own signing keys, and you're not really dependent on anybody else saying you have to.
And each of these partners in the supply chain, they could actually be using their own CA.
Exactly. It can be it can be multi-CA, it can be multiple key sizes, multiple key algorithms, and the more you put into this mix, the more difficult it is for any hacker to tamper with content.
Sure. Some of our manufacturing customers, building a single product, because they're building very big products. They may have 1,000 suppliers in their supply chain, delivering physical components, physical goods, electronic components, software components, all in there, right? Imagine an airplane being built, the number of vendors required. How do you validate all of that? Are they all going to have the same CA? Absolutely not. Do you want to be able to check each part? As many as you can, right? So this model starts to solve that problem. Okay. Now, we just have been talking mostly about update and a bit about enrollment. But when you look at the different components of where we can help, we're talking about providing tools that make it easier for developers to build more secure devices that can use a TPM or some sort of trusted identity or root of trust. And that's Mocana TrustPoint. That's all of our endpoint, IoT endpoint or embedded system software delivered as source code or binaries to help developers, device designers and developers. During the manufacturing and device activation process, TrustPoint will work with TrustCenter to enable and scale and simplify enrollment, digital certificate provisioning, all of those things you need to do to make sure you have a trusted identity that can be used. And that can be used then to do things like securing the updates, securing the update process, and securing OTA updates, and of course pairing that with any updates to the security on that device, the security life cycle, right? So all the way through to end of life. So it's a very powerful, comprehensive platform that's suitable for very large manufacturers to solve the supply chain issue. Ultimately, this is about solving a supply chain issue. Updates is just one piece of that. So, and we talked a bit about the challenges here. So, is this good just for we talked about it, about doing it, about this, about Mocana's approach to secure updates. Is this how is this helpful for both malware as well as other scenarios here?
Yeah, so the fundamental challenge with malware is really figuring out how it landed on the device. So once you have a stronger method for update management, it's more difficult for a headless device where users are not sitting browsing the internet or checking emails. The influx of malware because of user interactivity goes away. It's really a self-contained, locked-down, unifunction or purpose-built device. So it just blocks out the channels by which malware can land on the device. Because detecting malware on such devices is really a heavyweight operation, and you really have to design these devices to be more resilient to malware landing on them. So that you're defending against landing of malware, and that's really the first step. And malware can land also because of an employee error, an insider threat, or intentional or unintentional misconfiguration. So those can be handled because even configurations that are sent to the device can be sent over a secure update. If you are sending important information from, let's say, firewall rules or core configuration settings on a device where someone could turn off a certain setting that puts the device into an insecure state, those type of changes can also be done through a secure update, through scripts, and that really is a way for avoiding those configuration errors. And having multiple signatures, what we call as the multi-person rule, makes it difficult for a single bad actor to introduce an error intentionally or unintentionally. And the physical attacks are something that can be protected with secure update, because even if you were to send the update package on a USB stick to be inserted on site in an air-gapped network, what is on that USB stick can still be a PKCS11 sealed envelope, so that even that air-gapped network will be protected, even if there's a physical insertion of a media on a device. It could be something on an aircraft, it could be something deep inside a hospital system, and even that physical attack can be blocked by enforcing secure update.
Great. Well, thank you, Srinivas. Let's take a couple of questions. We have a couple of questions here. One question we have is, how do I implement Mocana secure update on the devices? How would they use it?
What we provide is clients that are installed on your device and a full service portal and a service. And you also have the option of API-based service connectors. So it's a very simple install on your device, and then you set up your service in your data center. It can be in the enterprise, it can be hosted in the cloud, and it's a very simple configuration of your backend connectors, your databases, your identity providers or certificate authorities of your choice. And once you have installed and configured this setup, then it goes into pretty much an autopilot mode.
Great. Well, that is all we have time for today. If you have any other questions, please be sure to reach us via our website And join us again on Tuesday, September 18th. We have another great webinar coming up with our partner Intel entitled Industrial Cybersecurity Zero-Touch Provisioning Virtual Conference. So it's all about how we're working with Intel to deliver zero-touch provisioning and automated security. It should be great. We hope you can join us for that, as well as a number of other, and that's on September 18th, Tuesday. And then we have several other webinars coming up later in September on IoT endpoint protection and lifecycle management. So with that, thank you very much, Srinivas, for your time today. And we will see you all at our next webinar. We hope you'll join us. Thank you.